And can you tell me a little, because give us a 2 minutes short introduction to the SETI Institute.
Yes, so SETI Institute started out in the 1980s to collect private donations to look for extraterrestrial signals. So it was started by a bunch of people, including Jill Tarter and Sasha Ostak and so on in the 80s. But then it kind of grew as a contractor for NASA. Because, you know, we have a big NASA center in California in Sunnyvale called NASA Ames, and SETI is right next to it. So we expanded to take over, so they hire postdocs through us. And then we also grow as a soft money institute, which is a very big thing in planetary science in the United States, that there is grant money, but people have to have an institution at which they would apply for grants and do research. So SETI is one of the top few planetary science and astronomy and astrobiology, but planetary science is the main thing. Soft money institute. So that's what I do. I have nothing to do with search for extraterrestrials. And most people at the institute have nothing to do with extraterrestrials. We just propose to NASA, and when we get funded, we do that research.
Okay. And how big is the institute now? Can you count? I mean, can you say?
I think we have about 50 PhDs. That's what people say. And not everybody is in California. We allow people to work remotely. It was before the pandemic. So minority of people are elsewhere in the US. And then we have some PIs working on NASA Ames site, especially the ones with labs. So they're officially SETI employees and their money goes through SETI, but their labs might be on NASA campus.
How long have you been there now?
Has been almost 10 years. That scares me to think about it. Time passes fast, yes.
San Francisco is home now, right?
Yeah, it is home. I did my PhD at Cornell, and then I was a postdoc in Vancouver at UBC. And I was then postdoc at Harvard. I was both at Earth Sciences there and at CFA.
And you like to do difficult questions, I see, difficult problems.
Well, I like to do orbital dynamics, and then easy things have been done. So what is left is hard.
Okay, good. So this is a very difficult problem, you know, in the solar system, which is the orbital evolution of the moon. The reason being that, you know, we know a lot about the moon, and then so we want to know a lot more, and we don't understand a lot more. So therefore, it's very happy to have Dr. Matija Cuk to give us this very interesting talk.
Thank you. So today I'll talk about the orbit and evolution of the moon. So first, I'll give you some intro of why the moon's orbit evolves. Then I'll talk about the classic picture, which goes back to the 60s. Then I'll talk a little bit about high angular momentum impacts. And I worked on some of those in the last few years. Then I'll introduce obliquity tides and why they're important. They're the crucial overlooked element of the tidal evolution. And then for some solutions for the problem of lunar inclination. So the orbit of the moon right now is rather large as satellite orbits go. So the moon is at 60 Earth radii from Earth. Orbit is eccentric, but not very much, about 5% eccentric, and it's inclined to the ecliptic. So the plane of lunar orbit is about 5 degrees away from the plane of Earth's orbit around the sun. While, as you know, Earth's axis is tilted about 23 degrees from the ecliptic. So that's the situation now, but hasn't always been the case. And we know actually the orbit of the moon is growing, and it's growing because of tides on Earth. So moon is rising tides on the ocean. And so this is a very naive picture I'm showing you. It's in reality, it's way more complicated. But the basic idea is that the surface of the Earth, including oceans, is deformed by the tidal field of the moon. And Earth becomes slightly egg-shaped because of the tidal forces. And as the moon rotates, the tidal deformation wants to get ahead of the moon. if there was no dissipation at all, it was perfectly elastic response by Earth and the oceans, the long axis of the egg-shaped Earth would always point to the moon. But because energy is lost in the process, and that's why we can have tidal energy, the long axis of the egg gets ahead of the moon, and then the torques between the deformed Earth and the moon act to pull the moon forward, giving it angular momentum, making its orbit bigger, while Earth is being pulled backward, slowing down rotation and taking away angular momentum from Earth. In this process, angular momentum is conserved to the system, but it's transferred from Earth to the moon. So the orbit of the moon gets bigger. And we think it grew from as little as 3 Earth radii when moon formed to 60 Earth radii now. The other kind of tide I won't talk much about is the tide within the moon, which basically acts to decrease the eccentricity of lunar orbit. This is an interesting subject, how eccentric the lunar orbit was over time, but probably it was always low eccentricity, probably lower than it is now. So just you should know that lunar tides always tend to decrease eccentricity, and they also do not change angular momentum of the orbit. Okay, so the beginning of our understanding of lunar tidal evolution, as often in orbital dynamics, starts with Peter Goldreich. He had a paper in 1966 that was semi-analytical, semi-numerical paper. In those days, computers could not integrate orbital evolution directly, but Goldreich made a model of numerical equations that describe precession of Earth and the moon around each other, and then integrated that using computer. So let's start with this picture here. What this plots is inclination of lunar orbit in the past. So right now we are here, 60 Earth radii. So the distance is on the x-axis, and distance was smaller in the past, as we know. And inclination is now about 5 degrees. So what Goldreich found is that as we go further into past, and when moon was closer to Earth, the lunar orbit and Earth's spin axis had to precess around each other. So that you had this thick zone covered by inclination, because there is not any more single inclination relative to the ecliptic, but the Earth's spin and lunar orbit will precess around each other. And then when you look at this other picture on the bottom, which is a lunar inclination to the equator, it's fat now. It's this fat line because these two bodies precess separately, Earth's spin and lunar orbit. So there's a range of mutual inclinations, but early on, the moon was close to Earth and the lunar orbit precessed around the equator. So you can see we get to the constant inclination of lunar orbit to the equator, and it was about 12 degrees, 10, 12 degrees, depending on the exact model. So Goldreich found that first, moon used to be much closer to Earth, and that the moon started out in an orbit close to Earth that's relatively close to the equator, but not quite, because it's about 10 degrees tilted. And also, obliquity of Earth was lower in the past. It was more like 10 degrees early on. So in 1994, Jihad Touma and Jack Wisdom wrote a follow-up, which used fully numerical approach and had multiple tidal models, and they accounted for the solar tides better now. But you can see that their picture, the one on the left-hand side, is, oh, sorry. Let me see if I can go back. Is basically the same as the right-hand picture in Goldreich, which just means that Goldreich got the right result, and we are still, using the numerical methods, we still get the same answer, that moon started out close to Earth, and that it was at a slightly tilted orbit. So that gave rise to the theory of giant impact, that we had to explain why moon started out close to Earth with a relatively large angular momentum, but little iron. So it's not made of the same material as Earth. So giant impact was invoked starting in 1975 to explain that the moon is formed from debris from the collision of two bodies. And this is one of the classic simulations of giant impact from the beginning of the century by Robin Canup. The impactor is completely destroyed. Most of its core goes into Earth, but much of its mantle goes into orbit. So early in this century, after giant impact became widely established, there was seemingly no problem with the orbital evolution. We all agreed what the orbital evolution was. People could not explain the composition of the moon, because as the isotopic makeup of Earth and the moon kept being studied with more and more precise methods, it turned out that moon is more like Earth than expected, if most of its material came from the impactor. Other terrestrial bodies like Mars or Vesta are way more distinct than the moon. Throughout all this, there was also a problem of the lunar inclination, which now it's 5 degrees. It used to be 10 or 12 degrees early on. There were several ideas about it, but they were all kind of putting a little fix to the giant impact. So I'm mentioning the isotopic crisis because it kind of led to big changes in the ideas about orbital evolution. So you can see in the classic giant impact, what Robin Canup did here, just before the impact, just before the impactor connected with Earth, she went forward in time, found out what different SPH particles were doing, and colored them depending on their future fate. And the yellow particles are the ones going into the protolunar disk. So you can see that most of the material that will in the future make protolunar disk in the simulation is comes from the impactor, not Earth. So you would expect the moon to largely inherit isotopic makeup of the impactor, but we know that Earth and the moon in many isotopic systems are indistinguishable. So that led Sarah Stewart and myself to propose that early Earth had much more angular momentum, and in the more energetic impact, more Earth material ends up in the disk. There have been different proposals that are similar. Since this is the same kind of plot on top, where we plot the material, where does the material in the disk come from? So yellow stuff are the particles that will go into the disk, and you can see that most of it comes from Earth, and a large chunk of the impactor, which in our idea is smaller, escapes. That's the red stuff, but disk mostly comes from proto-Earth. So this was a proposal to explain the isotopic makeup of the moon, but then we had to somehow solve the problem that this impact leaves Earth with much bigger angular momentum than it is found now, and as you know, tidal evolution conserves angular momentum. Yeah, and the other way to get this also is using two equal size impactors. They got completely mixed into Earth and the moon, which are then isotopically similar, but also we end up with too much angular momentum. So there are multiple processes that do not conserve angular momentum. So one is, for example, core mantle friction. It doesn't work for Earth, really. It works best for very slowly rotating planets like Venus. Then what we proposed in the 2012 paper, and it was previously proposed actually by Kohler and Yoder in the 70s, is the erection resonance between the sun and the moon. I'll talk about that shortly. And then there are various high inclination solutions that I'll talk at the end of the talk. So what is the erection resonance? So this diagram is geocentric. So Earth is in the middle, sun and the moon go around it. Sun really should not be going around it, but plotted this way, it's easier to see what kind of resonance it is. It's a resonance between the actual position of the sun, or the mean position of the sun, and the longitude of the long axis of lunar orbit. So it's not the sun and the moon really that go into resonance, but sun goes in resonance with lunar orbit. So the lunar orbit precesses in space. That means that the long axis is rotating over time, slowly. But if we had a fast rotating Earth with the moon orbiting very close to it, the equatorial bulge of this Earth would be huge, and would cause the orbit of the moon to precess fast. And in this case, it would be at certain distance. From Earth, it would be 1 year. So you can have one-to-one resonance between the precession of lunar orbit and the sun. And then you can have a huge exchange of angular momentum that goes from lunar orbit to Earth's orbit around the sun. So this is one of the plots from our 2012 paper. So the way it works is that the moon goes out, they are stuck in the resonance, and you can tell its resonance by eccentricity being high. The orbit stagnates for a while, even goes inwards until the resonance is broken. Here is the resonant argument on the bottom. You can see it vibrates around 180. And then the tidal evolution continues. The Earth's spin is lost in the process. The spin period gets longer, while the orbit of the moon doesn't really grow, even gets smaller for a while. So this was the original idea, and it worked for a certain parameters of Earth and the moon. So in that first paper, we used more or less current tidal response of Earth and the moon, which is not really correct because moon is now largely solid, and back then it must have been very much fluid. So we found this drop in the final angular momentum, so that this valley touches the current angular momentum. So we start from high up, and then in this plot we just show that over a range of this parameter A, which is relative strength of tides on the moon relative to those on the Earth. So on this side, lunar tides are stronger, and on this side, Earth tides. But in general, this is a very narrow range, and the realistic range is probably much larger A. And there has been work by Jack Wisdom and Zhengling Tiang since, where they explored a larger range of A's and found a second solution, which is kind of like erection resonance, but not really. So that might even work better. So that's one complete set of models that can change angular momentum of Earth-Moon system. So it's a lot like a classical tidal evolution from giant impact, except that there is this short period, very early on, in the first million years or so, where Earth and the moon are stuck in this resonance with the sun, and after that everything goes on as before. And also we need to have a way of explaining the tilt of lunar orbit. But the tilt was always small, so people thought a small fix would do it. But then came a paper by Irina Chen and Francis Nemo. The abstract came out in 2013, the paper came out in 2016. So just look at the top plot here. The black line is what the inclination of the moon should be doing over time as the moon migrates out. If we do not include so-called obliquity tides, I'll explain in a moment. But once obliquity tides are taken into account, you get the red lines, which show that inclination should drop over time. Now, this red line is not what happened, because we have a lunar inclination, that's the dashed line. So somehow we have to explain why the moon still has an inclination despite the obliquity tides. So what are obliquity tides? Well, the gravity of the planet always deforms the satellite, and even the satellite in a synchronous orbit will experience periodic tides if its spin axis is not straight up. So you can see the tidal bulge in a synchronous satellite that has obliquity will go up and down. So if you look at the near side, the blue shaded region, here tidal bulge is in the northern hemisphere and then got down to the southern hemisphere. So this north-south move of the tidal bulge dissipates energy. And the net effect of obliquity tides will be to damp obliquity. So it looks like all satellites should damp obliquity, just like they have evolved into synchronous orbit and should rotate synchronously with the spin axis straight up. But there is a problem with forced obliquity. not the one of the satellite itself, but it's being forced by other bodies. And that's where we get to Cassini states. And Cassini states have been worked out pretty thoroughly for synchronous planetary satellites. And most planetary satellites, like Galilean satellites, satellites of Saturn, and so on, are in this Cassini state 1, in which their precession period of their spin axis is much faster than the precession of the plane of their orbit. In which case, the satellite settles into a state where its spin axis is almost the orbital plane. Usually this angle here between the red arrow and the black arrow is very, very small for Io or Europa or so on. But instead of precessing in this picture, the spin axis of the satellite is very close to the orbital plane, but it's coplanar and on the opposite side of the Laplace plane normal. Laplace plane is the plane around which the orbit precesses. For close-in satellites of Jupiter and Saturn, it's the equator of the planet. For the moon, it's since many billion years ago, it has become the ecliptic, the plane of Earth's orbit. So close into Earth, this was the orientation moon was in. But when you are far from the planet, like moon is now, the Cassini state 2 is usually active, in which the spin axis is not close to the orbit normal, but it's close to the normal to the Laplace plane. To understand that is to think that the body's spin axis is precessing slower than the orbit, cannot follow the orbit, so then decides to start close to the kind of normal to the Laplace plane around which the orbit is precessing. But you can see that in this case, there will be a large angle between the spin axis and the orbit normal, which is the obliquity. So the obliquity tides will try to damp this inclination, but they can't do it because it's forced by their bodies. And then there was a transition between two Laplace states. This is a horrible, between two Cassini states. This is a horrible plot by Bill Ward from his 1975 paper. It's very hard to understand. But all you should see here is that at lunar distance of 30-something Earth radii, there was a switch between these two states during which moon must have had a very high obliquity for a short time. This plot was made without taking into account dissipation by obliquity tides. In our paper in 2016, we did take obliquity tides into account and found first that the inclination of the moon should damp a lot during this period. Then the moon will be in a non-synchronous state for a while because its obliquity will be so large, that it will be higher than 50-something degrees, which is the limit for stable obliquities. The bottom line is that once you take into account obliquity tides with a current non-dissipative moon, just a solid moon with the properties we have now, it should have damped a lot of inclination. So that idea that it started out with 10 degrees inclination is probably not true, but it started out with larger inclination, maybe even 30 degrees. So now our nice planar idea of the evolution of the Earth-Moon system just does not apply. And we have to explain a lot about lunar tidal evolution. So that's how we came up with the idea that maybe both angular momentum was lost and lunar inclination was excited during transition from the equatorial Laplace plane to the ecliptic Laplace plane. So if you look at a planet like Saturn or like Earth right now, there is a continuous stable reference plane for orbits. If you're close to the equator, if you're close to the planet, the reference point is plane is the equator. If you are far from the planet, it's the orbit around the sun, and there is a smooth transition. This works for planets that have obliquities below about 70 degrees. But for planets like Uranus, it's really not clear what is prograde, what is retrograde between orbits around the sun and orbits around the planet, because planet is tilted by almost 90 degrees. So there is chaotic region between planets close to the, so orbits close to the planet and orbits far from the planet. So if Earth had a large obliquity, then the tidal revolution of the moon would suffer instabilities that could potentially lose angular momentum. And that's what we proposed in our 2016 paper. It's extremely complicated, and these plots, strictly speaking, are all wrong. So I won't go into much detail on this plot, but I'll just say that we thought we managed to explain both the inclination of the moon and the loss of angular momentum by Earth starting at 70 degrees inclination, very high, obliquity, very high spin rate, 2.5 hours period. And we can end up with the present Earth-Moon system. The inclination of the moon is high at the end of the simulation, when the moon only gets to about 25 Earth radii, but we know it should damp later during Cassini state transition. However, last year, Shengli and Tian showed that our integrator had major errors because we leaked a bit of angular momentum. So we went back to it. So this is the correct version. It's the same process. It still has to come out. It's also a nicer one to look at. So you can see these numbers 1, 2, 3 that show different periods of high eccentricity, of excited eccentricity during this period. And those are all secular resonances between Earth, Moon, and the Sun. They're extremely complex. The one in the middle, that's labeled 2, is a form of quasi-resonance, for example. The 1 and 3 are similar in it that there are resonances between the pericenter and the node of the moon. And then there is also contribution from Earth's obliquity. So they're related to the quasi-resonance, but not quite. And since they include Earth's obliquity, they're able to damp the obliquity of the moon, of the Earth. So you can see we start with 65-degree obliquity, and in this case, it goes all the way down to 0. We probably needed to go down to like 15 degrees. It depends a little bit on tidal properties. We can lose angular momentum, and as it should be, angular momentum normal to the plane of the ecliptic is conserved, as it should be. So you see here, horizontal line is the normal angular momentum, and we start with much higher one, and through these secular resonances, we get down to almost planar system. So this is quite wild, and it's certainly not the final story, because every time we keep improving the integrator and putting in new physics, crazier stuff comes out. But I think that we cannot really go back to the 20th century idea of lunar tidal evolution, because one more thing to talk about. But this inclination problem has gotten much worse, and we really have to address it because of the work on recent work on obliquity tides. So just for completeness, I'll mention that there is another explanation for inclination that in the last few years, that moon managed to evolve out real fast due to the high dissipation in Earth, and managed to be at a high distance from Earth while the planetesimals are still around, and their flybys could excite inclination. There are issues with this concerning tidal properties of Earth and the moon, but you should know that this explanation is out there and should be looked at. So I hope I just managed to give you some of the history of the work on lunar tidal evolution. At first, we thought that lunar tidal evolution wasn't particularly interesting, and it was very important for first formulating giant impact hypothesis. But then kind of composition was a driver that made people think about ways of losing angular momentum and going through more exotic resonances during tidal evolution. And independent of that, we also realized that we have been underestimating lunar inclination in the past, because these early simulations did not include obliquity tides. And so what I'm working on right now, which I think is a promising avenue to explain both the composition and inclination of the moon is the idea that Earth-Moon system had a high initial obliquity and angular momentum, and during Laplace plane transition, it lost angular momentum and obliquity came to where it is now, explaining low obliquity of Earth. In a classic giant impact, low obliquity is just a kind of accident of the way giant impact happen.
Thank you so much. I think that this is, you make this very complicated thing looks, I don't know, what makes it look more complicated or look more simple, you know. And let me see. Anyone have questions for this? This very interesting problem. And let me ask the question first, because I think that I think it's logical because you want to explain the isotope composition issue, so you want to mix the material, the Earth material, into the disk, right? Into the protolunar disk, and to do that in your model with your Stewart in 2012, you need to have a very fast spinning Earth, so that it could so they spun the material outward. But the number, the rotation period of the proto Earth at the time is 2.5 hours. And how do you get that fast, spinning Earth?
Well, you would need a previous impact. So that was kind of a first shot. We didn't care about that so much about it at the time. We just wanted to see if you have a more energetic impact, if we can get more material in the orbit. There was the other proposal by Robin Canup that had equal size impactors. I think that basically all we need is angular momentum, and then things will happen by themselves. So the more recent work on the composition was by Simon Locke, who's a student who was until a year or two ago student with Sarah Stewart. Now he's postdoc at Caltech. They realized that if you have high angular momentum, the equator is almost in orbit. And also there is high pressure, and some of it is pressure supported, while the disk itself is sub-Keplerian because of pressure support. So there is no real boundary between the disk and the planet. So it might not be just that it's easier to launch material in an impact that has high angular momentum, like we did in 2012. Actually, that after impact happens, the material in the disk and Earth's mantle could mix much more easily, because there is no dynamical boundary between the disk and the mantle. So this donut-like body surrounding Earth that's in communication with its mantle, we call synestia, and we think that that's kind of the answer to the composition. That if you have enough angular momentum, you get a new kind of astrophysical object that's not really a disk. It's fat, and it's although it has small amount of mass, it's connected to the central body.
Okay, that's when I think I think there are a number of talks. I mean the Sebastian Chanos, he gave a couple talks already about this donut-shaped disk structure. Now, anyway, the moon has to form, right, one way or the other, and then supposedly people also talking about that even after the proto-moon was formed, it was covered by a magma ocean.
Yeah.
So that for the people who are working on the crater and things like that, they're very interested in the cooling of the magma, the lunar magma ocean. So the question then is that at the same time you have this very violent, I would say violent angular momentum transfer, and there must be also involved with energy dissipation. And how would that affect the magma ocean energy budget?
Yeah, so basically, we won't have the moon fully solidify for more than 100 million years in this model. That's a direct consequence. And we assume that the moon is basically fluid and is deformable. That way, it can dissipate more energy. The high obliquity behavior would not work if Moon would have been solid already. That it works. So I think that the mechanisms of angular momentum laws that still work are the ones in which Moon is very dissipative and hasn't solidified yet. So that's the evection limit cycle by Tian, and also our high obliquity stuff. And the original evection, in which we had high eccentricity of the Moon, but it was relatively non-dissipative, is not really realistic because it would melt.
Okay. Any other questions to Matija? So I think that your future work would be in which direction, as you say here?
Well, we are trying to get this paper published with the kind of fixed integrator, but also we managed to kind of look at it in more detail, because the original 2016 paper tried to look at all the stages of evolution from the beginning to the end, and it was quite something in a Nature paper. So now we're able to look at the individual secular resonances, and it's really complex, but we are understanding why these things happen. Like, once you have a resonance, you can do almost anything. So I hope that understanding the details of the process will help us figure out, like, what are the parameters within which it can work. So so after this, I'm still thinking about what could be next. Let's see also what other people are doing.
Oh, very good. It's very impressive, I must say. You know, that you can think of all those kind of interesting things. I'm sure you will have a lot of things to do, you know, in the coming years. Okay, if not, let's then finish this talk for now, and I'm sure that we will ask you coming back now to give another talk.
Yeah, thank you. Thanks for inviting me. It was very nice.
Yeah, I mean there's actually, this is even though it's very short, you know, it's not long enough, but clear, and it's a good start, you know, for us to. It's not easy to find people to talk about the lunar orbital evolution. So it's lucky that we can find you agreed to give this talk, and thank you again. Thank you so much.
Thank you.